This video follows Chapter 11 if you have the Modern Refrigeration book, 20th edition. So in this chapter, we're going to be talking about working with refrigerants. Now, we're going to outline a lot of the different service tasks. We're going to sort of summarize some of them, and we're going to summarize some of the procedures that you will entail when you're working with refrigerants. So we have several objectives of what we want you to be able to do. We want to be able to check the refrigerant charge by determining a system's superheat or subcooling. We want you to be able to implement both passive and active refrigerant recovery procedures. We want you to understand how to charge a system with an inert gas to pressure test for leaks. And we want you to be able to carry out refrigeration system leak repairs using either epoxy resin or brazing. And we don't like using epoxy resin, so the correct procedure basically is brazing. We want you to be able to evacuate a refrigeration system using both a deep vacuum and a triple evacuation method. We want you to be able to charge specific amounts of refrigerant into a system as either a liquid or vapor. And we want you to be able to follow approved safety procedures when recovering and charging a refrigerant. You don't want to hurt yourself ever while doing work. So we all know through prior conversation that proper refrigerant charge is necessary for proper operation. When you have an undercharged system, the compressor may operate continuously. It produces poor refrigeration. Moisture may be released from the dryer into the system, okay, because the vacuum will be the wrong direction. Overcharged systems, you have excessive head pressure. And you can have possibly severe compressor damage if you start getting liquid in that compressor. Compressors are not designed to pump liquid. They're vapor pumps. So subcooling is one of our measurements that we can use. Subcooling is the amount of heat removed from refrigerant after condensing. Subcooling equals temperature drop from a liquid line to the condenser. It's determined by a thermometer or a high pressure gauge with a PT chart. It's used to check charge in systems where a thermostatic expansion valve metering device. Okay, if you have a TXV or actually an EEV, you're going to be checking with subcooling. Now there's one exception. If your system has a receiver, subcooling will not work as a method of checking a charge. So just be aware of that. If your most split air conditioning systems and package units do not have a receiver, it's probably an accumulator you'll find if it's a heat pump system. But if your system has a receiver, that's going to be between the condenser and the metering device. You cannot use subcooling because it's not going to give you good readings. So to check the refrigerant charge by subcooling, what you're going to do is you're going to determine the condenser temperature, you're going to determine the liquid line temperature, and you're going to subtract the two. So subcooling equals condenser temperature minus liquid line temperature. We want to be able to compare the calculated values with manufacturer specifications. The other method to use is superheat. The amount of heat added to the refrigerant after it has evaporated. We can use superheat to check refrigerant in any system with a fixed type metering device. This would be a cap tube, okay, fixed orifice, flow check piston. All of these types of systems we can use superheat to check refrigerant charge. Now the reason this doesn't work well with TXVs is TXVs are designed to maintain a superheat. So even if a system is slightly undercharged or overcharged, the TXV will maintain that superheat as much as possible. So if you have a TXV or an EEV, any device that senses suction line temperature and does superheat calculations, they don't do well with superheat as a way to verify charge. Again, one exception, if you have a receiver, you really don't have much choice. You have to use superheat. So to check the charge by superheat, measure four values. You're going to measure the dry bulb temperature at the condenser. You're going to measure the wet bulb temperature of the return air just before the evaporator. You're going to measure the pressure of the refrigerant in the evaporator. And you're going to measure the temperature of the refrigerant at the suction line service valve. Now, the pressure of the refrigerant in the evaporator, you need to convert to temperature. So to calculate the superheat, you're going to take the suction line temperature and subtract from that the evaporator temperature, which should be cooler. Okay, superheat, suction line temperature minus evaporator temperature. Evaporator temperature is your low side gauge converted to temperature. Once you find the superheat, you want to find the chart that's on most units right inside the wiring cover or in the manufacturer directions. You can also use a standard chart that's pretty much applicable for all systems. Okay, you want to compare your calculated value with the target superheat for the measured wet bulb and dry bulb temperatures. Why does wet bulb matter? Because a good portion of our air conditioning is removing latent heat. So let's say I have a hot day outside, 95 degrees, and my return wet bulb temperature is 66 degrees. I should have a 10-degree superheat. Okay, so we just need to be very aware that wet bulb temperature on the return air going across the coil does matter. In the past, people did not take this into account, but wet bulb does matter. To pump down a refrigeration system is another task you're going to do. You're going to basically pump down means to relocate the entire refrigerant charge into the liquid receiver or the condenser. Okay, we can use this method to repair leaks, we can adjust low side pressure controls, and we can replace components because we've isolated the refrigerant between the compressor and the liquid line service valve or the king valve. Now, if you're doing this on a split system air conditioning system, you have to make sure that that condenser is large enough to hold all of the refrigerant. A lot of times it is not. So do not really do this automatically unless you have a receiver or a very large condenser. You have some active recovery methods. You either use active recovery, uses a recovery machine, and it pulls out the system's charge, or you can do passive recovery, which uses the system static pressure, which forces vapor refrigerant into unpressurized recovery cylinders. This is used on smaller systems. Most technicians will be using active recovery using a recovery machine. Passive recovery, basically, the internal pressure forces the vapor into recovery bag until the pressure equalizes. If the compressor works, you can pump the remaining refrigerant into a bag. If the compressor does not work, you can put the bag on ice and you can then raise the temperature of the refrigeration system and the refrigerant will migrate to the lowest point. Again, this is not used very often. Vapor recovery is an active recovery process. The vapor refrigerant drawn out of the system through the gauge manifold. Refrigerant is pulled from the low side and high side together. Vapor flows through the inline filter dryer and vapor enters the recovery machine. The recovery machine's compressor pumps the vapor through its condenser, and liquid refrigerant then flows into the recovery cylinder. Setup for vapor recovery, again, high side mid position, low side mid position, both low and high side gauges open, okay, and then you connect to the recovery machine. This is the method that primarily you're going to use when you recover refrigerant. You're going to recover from both sides. Liquid recovery, again, is an active recovery process. You recover liquid refrigerant from the high side of the system. It's a little bit faster than vapor recovery, but it must be followed by vapor recovery to remove the entire charge. Don't use liquid recovery methods on heat pump systems or systems with less than 10 pounds of refrigerant. Again, most often you're going to recover from both sides of the system at one time. Setup for liquid recovery, same setup, but you're not going to open the low side valve in your gauge handles initially. You're just going to open the high side valve. The recovery machine will pull the liquid out first. Again, don't use this on heat pump systems because the check valves in the heat pump systems will prevent this from working properly. Push-pull liquid recovery. The recovery machine creates pressure. It creates a low pressure in the recovery cylinder. It pulls vapor out of the cylinder. pumps high pressure vapor into the system, pushes liquid recovery into your cylinder. Vapor recovery has to be followed. Again, this is not used very often. This is not a recommended method for recovery, but some people use it on heat pumps. Okay. Basically, what you're doing is you're putting a series through the recovery cylinder. Probably is not something we want to recommend. We want to use large hose diameters. Okay, we want to use as short hoses as possible. The shorter hose, the less pressure, quickens vapor travel. It produces less resistance and pressure drop. You want to remove Schrader valve cores using Schrader valve core removers. We want to place an inline filter dryer between the refrigeration system and the recovery machine's inlet port. After using a recovery machine to recover refrigerant from a burned out system, if there's compressor oil in there, change it. That oil is contaminated. Recovery cylinder capacity is relatively important. It's the maximum amount of liquid refrigerant the cylinder can safely accommodate. So the water capacity is the weight of the volume of water needed to fill a recovery cylinder. The fill level is 80% of the water capacity by weight. Take refrigerant density into account. So your weight of your full contents, the weight of the contents that you can fill, is 0.8 times the WC rating times the specific gravity of the refrigerant if you know it. If not, just go with times 0.8, WC times 0.8, which is 80% of the water capacity. So again, you have a tear weight, TW, that's stamped on the cylinder. You have a water capacity that's also stamped on the cylinder. Adjust the scale to 0. Okay, that takes care of the weight of the cylinder. If the scale cannot be zeroed, add the cylinder's tear weight to the equation. So your WC, which is your weight of contents that you can add, is 0.8 times WC times the specific gravity plus TW. Again, if you do not know the specific gravity of the refrigerant, just add the tear weight. For safety, on recovery, you want to monitor the amount of refrigerant in the cylinder. Sometimes a scale may sound a signal to stop or may close a solenoid valve. Liquid level switches or high pressure switch turns the machine off when 80% full. But it's best to monitor and turn off the recovery machine manually. Do not ever leave a recovery machine running when you are not present. Okay, you can't leave a recovery machine running and go to lunch. Locating and repairing refrigerant leaks is important. Leak indications could be low head pressure, low suction pressure, lack of cooling. You can also find leaks by looking for oil. Okay, all methods include a pressurized system of locating leaks. If a system has no pressure, technicians must add pressure to find a leak. You're not going to find a leak in an empty system. So to add pressure to a system, you want to create a positive pressure of 5 to 30 psi. Okay, now with larger systems, okay, and the newer systems, you want to find the unit label and look for the test pressures on the low side of the system. Okay, find the test pressures for the evaporator portion of the system. You never use fuel gases or oxygen or compressed air to pressurize a system. They cause an explosion hazard. Oxygen does not do well with refrigerant oil and sparks. Use inert gases such as nitrogen or carbon dioxide. Most technicians use nitrogen. Charge the system with inert gas. Evacuate the system and charge again with an inert gas and a trace amount of a specific refrigerant. Used if the leak cannot be found, it allows the use of all methods of leak detection. EPA allows refrigerant release as leak test gases. Okay, here's the deal. Charge it with nitrogen first, okay? If you cannot find the leak with nitrogen using like soap bubbles, looking for oil, listening, Okay, you can put a little bit of refrigerant into the system so that you can use an electronic leak detector. That refrigerant, as long as it's used as a leak detection gas and it's mixed with nitrogen, does not have to be recovered. Okay, so what you're going to do is to charge with an inert gas, you're going to use your nitrogen cylinder, have to use a regulator that includes a pressure relief valve, and you're going to connect the system to the system. Most often here, you're going to put your gauge set. Always install a pressure regulator and a pressure relief valve between the cylinder and the system with pressure testing for leaks using nitrogen or carbon dioxide. Again, most of your regulators now on nitrogen tanks come with internal pressure relief valves. It's recommending testing pressures are not known, do not exceed 170 psi when testing with carbon dioxide or nitrogen. Be sure the pressure regulator is accurately calibrated. The relief valve should open at 180 psi. And right now, again, with the newer systems and the newer refrigerants, that relief valve is much higher. That's why you want to use the one on your regulator. Recover refrigerant from an affected part of the system. Check system pressure. Purge the system with flowing nitrogen 1 to 2 psi through the brazing area during repair. Okay, so let's say you have a leak here near this just happens to be a heat pump system. Okay, and this is where the reversing valve is. Let's say there's a leak on the fitting of the reversing valve. You absolutely want to just take out the Schrader cores because you're going to disconnect your gauges, and you're going to flow 1 to 2 psi of nitrogen through this system while you're brazing. Now, what that's going to do is that's going to reduce the internal oxidization of the line sets. Do not braze anymore without nitrogen. Okay, because you'll find that there's debris that starts entering the system that can clog orifices and distributor lines. However, when you braze with nitrogen, you do have to have a little bit of a hotter flame. While we don't recommend it, epoxy resin is a way to seal leaks, okay? It's thermosetting polymer that forms a strong adhesive. It's used to repair cracks and leaks in evaporators and joints. It's used with aluminum, steel, copper, and plastics. Two-part systems are most effective, okay? Now, again, we do not recommend this. This is not the correct way to repair leaks unless you can absolutely avoid it. Sometimes you might use it on an aluminum tubed evaporator. Okay, but again, this is a short-term repair, and this is not something you want to do on a permanent basis. When using epoxy resin, avoid contact with skins. In case of contact with skin, remove the epoxy, clean skin with rubbing alcohol or a waterless soap. Wash thoroughly with soap and water. Do not let it stick your fingers together. Okay, to evacuate a system following the repair, what you're basically talking about is removal of vapors, gases, and fluids from a system. When to evacuate? After refrigerant has been recovered and before system is charged. The evacuation methods is a deep vacuum or triple evacuation, and we'll talk about both. We always use a vacuum gauge, or we can use our gauge sets if they're digital and read microns. So you can have leaks and moisture on an evacuate system pressure. Okay, if you have missed a leak, okay, what's going to happen is once you have evacuated the system down to your 500 microns, you shut off the vacuum pump, close your gauges, and you're going to see a consistent rise in pressure over time. Okay, that means there's still a leak in the system. If you have moisture in your system, which basically means you still have to run the vacuum a little bit more, what you're going to see is the pressure is going to rise but then level off at a point higher than your target evacuation. So again, a straight line slanted rise in pressure over time means you have a leak, okay? If the pressure rises and levels off, you don't have a leak, but you still have moisture in the system. Watch your gauges and be able to identify this. So a deep vacuum, the vacuum pump has to be able to pull down to 250 microns or deeper. It uses service ports and access ports. You cannot use piercing valves, and you want to remove the Schrader valve cores. On deep vacuums, we want to continue until no more moisture or vapor remains. We want to be able to use a vacuum gauge to determine if the system has moisture or leaks. The vacuum should hold at 500 microns for at least 1 minute. And honestly, once you have it to 500 microns, you want this to hold longer. Now, while the slide does not say this, one of the things you always want to check is make sure your hoses are good on your gauge sets. A number of years ago, we ordered a batch of hoses at the school we're at school, and there was pinholes, little pinholes in the hoses on the high side. Not enough where we were seeing for refrigerant leaks, but we could never get the systems into vacuums. Okay, and we turned out we actually put the hoses under extremely high pressure nitrogen. I think we used 600 psi, and then put them in a tank of water, put them in a trash can of water, and we were able to see the bubbles. But if for some reason you can't pull a proper vacuum, check your refrigeration gauge hoses. To set up for deep vacuum, real easy. You have a low side and you have a high side. Okay, you open both sides on your gauge sets, you put a vacuum gauge in line, or if your gauges are digital, you can, and do microns, you can use the digital gauge on there. Okay, we attach a vacuum pump and we let it run. Triple evacuation means that the vacuum pump pulls a vacuum of 1500 microns 3 separate times. The system is charged with a small amount of nitrogen after first two vacuums, and the moisture remaining in a system is absorbed into nitrogen and pulled out of the system. Now, once again, this has been updated for the newer refrigerants. Okay, we don't want to pull the third time, the final vacuum. We still need to pull it down to a 500 micron vacuum. That is a standard. You have to achieve that. Set up for triple evacuation. Okay, basically we use a nitrogen cylinder, okay, or refrigerant sometimes to match the refrigerant in the system. We do a first evacuation, pull it down to 500 microns. We shut off our vacuum pump. We charge a little bit of nitrogen back into the system. We then shut the nitrogen off. We turn the vacuum pump back on, and we do this a total of 2 times. On the third vacuum, you need to pull down to 500 microns. Once you have the system in a vacuum and a deep vacuum, you add refrigerant back to the system to charge it. It must be done after the system is opened, repaired, and evacuated. Symptoms that other charging may need it is a partially frosted evaporator, low side head pressure, low side pressures, a leak, or system that short cycles. Now, just a few additional notes on this side. If the system contains a zeotropic blend, remember that's the blend that will fractionate as it leaks out of the system. Okay, and I basically want to say if the system contains a refrigerant that is a blend, if there is a low charge, if you suspect there's a leak, you have to recover all the refrigerant out of the system. You cannot just top it off. Liquid charging's faster, but involve risks. And again, this slide is based on non-fractionating, non-blended refrigerants. Most systems should be vapor charged unless you're using a refrigerant that is a blend. Do not charge a blended refrigerant as vapor. And you can find that out by looking at the side of the container of refrigerant. If it says you have to turn the tank upside down, or you have to charge as a liquid, it will say it right on the cylinder. So vapor charging, you place this refrigerant cylinder update, you charge to the system's low side. Liquid charging, turn the cylinder upside down, charge refrigerant into the high side if the system is not running. If the system is running, you have to charge it slowly into the low side. You cannot charge a refrigerant into the high side of the system if the system is operational. For vapor charging, again, refrigerant cylinder is right side up, or you're connected to the vapor side of your recovery cylinder. Again, do not do this with blended refrigerants. Initial setup for liquid charging, your cylinder is upside down on the charging scale. Turn it upside down, let it settle down, and zero the scale before you start charging anything so you know how much refrigerant you're putting in. If the system is not running, you charge into the high side. If the system is running, you have to slowly charge into the low side. When you're charging a running system, always watch the amperage of the compressor. It's very important. Local building codes may specify types of refrigerant that can be used. It's most often having to do with flammability. Updating existing systems to new standards, replacing specific components is called retrofitting. Okay, identifying refrigerants, do not identify by color or smell if you don't know what's in the system. Use a refrigerant analyzer or turn the system off, let it stabilize to ambient temperatures, okay, that's temperatures around the system, and use a temperature pressure chart. Take the temperature of one of the line sets and take the pressure of that same line set. Okay, so high side temperature, high side pressure. Go to your temperature pressure chart and see where the two lines meet. A lot of times you can identify refrigerants by the temperature pressure relationship. Okay, modifying or replacing system components, contact the manufacturer for details. Do not be a mechanical engineer if you are not qualified to be one. Always go back to the manufacturer. There's a liability that you have as a technician or a contractor if you change things without manufacturer approval.